Hello everyone, my name is Pranno. I'm a research fellow at the University of Calabria in Italy, and I'm going to present a numerical investigation based on a cohesive fracture approach to analyze the degradation of the vibration characteristics in reinforced concrete beams induced by damage phenomena. It is widely known that the fracture phenomena affect significantly the global mechanical behavior of the reinforced concrete structure, and that the adoption of damage detection techniques decrease the risk of catastrophic failures. Therefore, the structural health monitoring is gaining more and more importance in the last years. For instance, the vibration-based technique founded on the concept that the damage will alter the dynamic properties of the structures represent an effective tool to detect the occurrence of damage phenomena by measuring the dynamic response of the monitored structure. This work employs a model-based technique, which is based on the comparison between the dynamic response of the structural system predicted by a numerical model and the vibration response, which is obtained experimentally on the real structure for a given ambient excitation or forced excitation. In this slide, the static and the dynamic damage indicators are briefly recalled together with the related references. The indicators highlighted in red are those adopted to detect the damage in this work. The first one, the inverse eigensensitivity method, which is based on the natural vibration frequencies, and the other ones, the model curvature and the curvature damage factor, are both based on the curvature of the mode shapes. Here, I'm going to describe the adopted numerical fracture model, which is based on the combination of two different numerical techniques. The first one, the diffuse interface model, that allows to capture the nonlinear cracking behavior in the concrete phase, and the second one, the embedded truss model, that allows to capture the interaction between the concrete and the steel bars. The novelty of the proposed implementation consists of a modified exponential traction separation law, which is able to take into account the contact phenomena between the crack surfaces during the loading process by means of a residual plastic deformation highlighted in red, delta Piane, which is defined as a fraction of the maximum vertical displacement, normal displacement, and a plastic stiffness highlighted in green, the KNP. In addition, a contact stiffness, KC highlighted in blue, is defined to simulate an intermediate condition between the opened and the closed crack condition during a compression phase. Well, here I'm going to show you the geometric configuration and the boundary condition and the material properties of the reinforced concrete beam subjected to a 4-point bending test with reference to the experimental test reported in Ahmad et al., which is published in the 2015. Below is also reported the mesh discretization of the numerical model that is based on a Delaunay mesh. And we can see that to reduce the computational efforts, the cohesive elements are inserted all in the region highlighted in blue, which is dominated by the tension and the shear stresses. In this slide, the results of the static analysis are reported, and 10 different damage levels are identified to investigate the degradation of the vibration characteristics for increasing damaging level. The first one it corresponds to the undeformed configuration, L1, and the last one corresponds to the 95% of the failure load, L10. The load versus midspan deflection curves highlight a good agreement between the numerical and experimental results. And for each level of damage, the unloading process is investigated and the related curves are reported in gray. In addition, an example of the loading and the unloading processes are reported in the animation on the right. Here, the natural frequencies and the related mode shapes are reported for both the undamaged and the damaged configuration of the reinforced concrete beam. They are obtained by solving a linearized eigenvalue problem superimposed on a solution of the static analysis corresponding with the investigated level of damage. As you can see, the natural frequencies decrease as the level of damage increases, but the presence of damage does not alter the associated mode shape. In addition, the curves on the right show a general decreasing trend of the normalized frequency, highlighting a greater frequency reduction between the 15 and the 50% of the failure of load. Here, the comparison with the experimental data shows a good agreement between the numerical and the experimental normalized frequency, especially for the first two mode shapes, since they are typically affected by lower uncertainties deriving from measurement error and dispersion of the experimental data. The frequency reduction are evaluated for both the loading and the unloading processes, and we obtained a frequency reduction of about 35% for the first one and of about 15% for the second one, highlighting that the frequency reduction during the unloading process is significantly lower than the loading one by virtue of the stiffening effect given by the partial crack closure phenomena, which is effectively simulated by the proposed model. Now, here in this slide, we can see that the result with reference of the modal curvature indicator. On the top of the graphs, I reported the damage map obtained at the highest level of the damage, and the dashed line are placed with reference to the macro cracks. Therefore, we can observe that the curves related to the highest level of damage show an oscillatory trend, deviating from the curves related to the undamaged configuration in correspondence of the macro cracks. In addition, we noted that the effectiveness of the modal curvature in detecting the damage phenomena strongly depends on the investigated mode shape. For instance, as you can see in the highlighted area, the cracks near the supports doesn't influence the modal curvature of the first mode shape here, but on the contrary, they strongly influence the modal curvature of the fourth mode shape. Therefore, to detect effectively the damage phenomena by means of such dynamic indicator, more than one mode shape should be analyzed. Finally, in this slide, two curvature damage factors are analyzed. The first one on the left is obtained with reference to the first mode shape, while the second one on the right is obtained with reference to 5 mode shapes. As can be seen, the first curvature damage factor is less effective than the second one. In fact, in proximity of the supports, the first curvature damage factor is not able to detect effectively the damage phenomena. On the contrary, the curvature damage factor on the right clearly show the location of the macro cracks near the supports, except in correspondence of the load application, where both the curvature damage factors resulted to be strongly affected by the presence of the stiff plates where the load are applied. Well, in conclusion, we proposed an effective numerical model for damage detection in reinforced concrete structure, which can be used as a pseudo-experimental system for monitoring the state of the structural integrity. The reliability of the proposed methodology is verified by means comparison with experimental results. And we observed that among all the investigated dynamic indicators, the curvature damage factor is the most effective also to detect the location of the damage phenomena. Definitively, the proposed model, by virtue of its accuracy and completeness, can be adopted in the context of the damage identification procedures. Thank you for your attention.